You know, every time you click, every show you stream, every message you fire off, it doesn't start in some magical cloud. Nope, it starts in a wire. Today, we're going to get our hands dirty and dive into the physical layer of the internet, the real, actual hardware that makes our digital world a reality. Let's get to it. We've all done this 1,000 times, right? You grab an Ethernet cable, you plug it in, and you hear that super satisfying click. It just works. But have you ever stopped to think for even a second, what is really going on inside that little plastic and copper cable? What kind of magic is happening in that split second that connects you to, well, everything? That's what we're going to find out.
You know, it's a step we totally take for granted, but it's the most important one. Because before a single piece of data can move, before you can watch a movie or send a single email, a real, physical link has to be made.
Now that connection might be something you can see and touch, like that Ethernet cable running from your computer to the wall. Or it could be totally invisible, just radio waves flying through the air from your phone to a Wi-Fi router. But here's the thing, whether it's wired or wireless, you're interacting with the physical layer.
But that simple click of a cable or your phone finding a Wi-Fi network, that's just the very, very top of a massive iceberg. Underneath that simple act is this whole world of incredible engineering that allows all our different gadgets to actually talk to each other. So let's pull back the curtain on this whole thing. That connection you just made, it's not just random. It's actually the very first step in a super organized 7-layer system that runs all network communication. And we're starting right at the bottom. Okay, so check out this diagram. This is the stack that makes networking possible. Think of it kind of like a set of Russian dolls. When you want to send something, your data starts at the top, at the application layer, and it travels down, getting wrapped in another layer of information at each step. We're starting our journey way down at the foundation, layer 1, the physical layer. This is where the magic happens, where digital bits become actual physical signals. So what's its job? Well, it's beautifully simple, but it's also unbelievably important. The physical layer takes a fully packaged chunk of data from the layer above it, just a big old frame of ones and zeros, and its one and only job is to translate all that digital code into a physical signal that can actually travel across a wire, or through the air, or down a tiny strand of glass. So, the big question is, how? How in the world does it do that? How do you turn a 1 and a 0 into something, well, real? It all comes down to speaking a very specific physical language. And we can break this language down into 3 main parts. First, you need the actual hardware, right? The physical components. Second, you need a shared code, sort of like a grammar, that's encoding. And third, you have to actually speak that code, that's signaling. Let's break them down one by one. All right, first up, the physical components. This is all the stuff you can actually touch. We're talking about the network card in your computer, that little plastic connector on the end of your Ethernet cable, and the tiny copper wires inside it. This is the physical stage where a whole digital drama plays out. Next, we've got encoding. Now, if the ones and zeros are like musical notes, you can think of encoding as the sheet music. It takes what would just be a chaotic jumble of bits and organizes it into a nice, predictable pattern. This makes sure that the device on the other end knows how to read the music correctly. Here's a perfect example of that. It's called Manchester encoding. Look at the waveform here. To send a 1, the voltage actually drops from high to low. To send a 0, it does the opposite. It rises from low to high. So it's not the voltage level itself that's important, it's the change, the transition. It's a super clever trick that basically works like a built-in metronome, keeping both devices perfectly in sync. And that brings us to our last part, signaling. If encoding is the grammar of the language, then signaling is the actual voice. It's how those ones and zeros are physically put onto the medium. It's the sound of the language being spoken. And this is where it gets really, really cool. On a normal copper Ethernet cable, that voice is a pulse of electricity, a little zap of a specific voltage. But on a fiber-optic cable, the signal is literally a pulse of light, blinking on and off millions of times a second. It's the exact same digital information, just being spoken in 2 totally different physical languages. How cool is that? Okay, so we have our signal, we know how to speak the language, now we got to get that signal from point A to point B without it getting all scrambled up. So let's zoom in on the most common highway for these signals, the good old copper cable, and see what it's up against.
Sending a tiny electrical signal down a copper wire is actually a really dangerous trip. I mean, first off, the signal just naturally gets weaker the farther it goes. That's called attenuation. Then you've got interference from things like power lines or even your microwave oven that can corrupt it. That's EMI and RFI. And to top it off, the signal from one wire inside the cable can actually leak over and mess with the signal in the wire right next to it. That's called crosstalk.
Let's see what that actually looks like. Okay, top left, you've got your perfect, clean digital signal. That's what we want. Top right, that's some random interference, some electrical noise. And when those two get mixed together on the wire, you get this messy, corrupted signal on the bottom left. And here's the problem. Look what the computer on the other end reads on the bottom right. That interference was just enough to make a high voltage 1 look like a low voltage 0. And just like that, your data is wrong, it's corrupted.
So how do we fight back against these signal-destroying enemies? Well, with really clever cable engineering. We're going to look at the 3 main types of copper cables that are designed to do just that. Unshielded twisted pair, or UTP, shielded twisted pair, STP, and coaxial. Each one is a different level of defense.
UTP is probably what you're using right now. It's definitely the most common network cable out there. And its secret weapon is the twist. Seriously. By twisting the 2 wires in a circuit around each other, their magnetic fields actually cancel each other out. This little trick massively reduces both crosstalk and outside noise. So simple, but so effective.
Now, what if you're in a place with a ton of electrical noise, like a hospital or a factory? Well, then you bring in the heavy-duty option, shielded twisted pair, or STP. It takes those same twisted pairs and wraps them in a metallic shield. This shield acts like armor, blocking out interference. Of course, all that extra protection means it's also more expensive.
And finally, there's coaxial cable. You've definitely seen this one. It's what probably brings cable internet or TV in your house. It has one big copper wire right down the middle, and it's protected by layers of insulation and a metal shield. That design makes it super tough against the interference and really good for carrying signals a long way.
Okay, so we've gone through the theory, the bad guys and the good guys. But let's bring this all home and see why the physical quality of something as simple as a cable is just absolutely critical.
Just look at this. This picture says it all. On the left, you've got a cable that was put together poorly. See how the wires are all untwisted? That completely defeats the purpose of that brilliant twist design we talked about. It's like leaving the castle gate wide open for interference. But on the right, it's done perfectly. The twists go all the way to the end. The connection is solid. That one tiny detail that you'd probably never even notice, that can be the difference between a crystal clear video call and the choppy, buffering nightmare.
So what's the big takeaway here? The next time you plug in an Ethernet cable or hop on a Wi-Fi network, just take a second to remember everything that's happening under the hood. Every single thing you do online, your work, your movies, your conversations with friends, is literally riding on a physical pulse of electricity or light, traveling through a carefully designed cable, all governed by these incredibly precise rules. The whole vast, abstract world of the internet, it's all built, quite literally, on this very real, very physical